Welcome to the next video in the series on condensed matter theory. And this is actually the last video where I want to talk about the Sommerfeld model, where electrons can move freely through vacuum, where electrons don't interact with each other, nor with the nuclei of the atoms that they leave behind, except for some mysterious form of scattering that we have introduced in the Drude model, with an average time tau between two scattering events. Now, this metal, with all its simplicity, can actually already explain quite a lot of material properties. We have seen that we can explain Ohm's law, Hall effect. Once we go to the Sommerfeld model beyond the Drude model, we can explain also thermal conductivity, the ratio between them. You can use this to explain things like Peltier elements, thermal electro effects, and the interaction between them. The model, however, doesn't explain everything. First of all, the richness of metals is much larger than you could explain within this model. The question why silver, gold, and copper get to their colors is not something you can explain within this model. And then there are also a few properties that are actually weird when you look in this model. And the first is the time between two scattering events. If you take the speed at which electrons travel, their Fermi velocities, then this means electrons travel by 10 to the 7 or even more atoms before they scatter. So somehow electrons don't really see the interaction with the lattice or with the atoms. Only very sporadically they scatter from them. And in order to understand the scattering mechanism better, you can actually look at different samples of copper, and you will find that at low temperatures different samples have a slightly different resistivity and a slightly different scattering rate. And you can actually find that a part of that scattering rate is temperature dependent and a part is sample dependent. And the better you make your quality, the smaller the sample dependent resistivity becomes. So you might even assume that at zero temperature the scattering length becomes infinite, which of course is hard to understand. Where then does the scattering come from? And another open problem that we have is the question on how much charge carriers do you have? For the alkaline metals, you can easily assume that this is 1 electron per atom because that's what sits in the outer shell. When you want to do this for something like copper, here, where we have all our d electrons, or nickel or cobalt, then it's not so clear what n should be. For copper, it turns out n is roughly 1, and it's not working perfectly anymore. For the alkali metals, the values from the Hall resistivity are much closer to integer numbers. And for aluminum, it becomes really weird, because there n is -1. Or the charge of the charge carriers has the wrong sign. Remember that the Hall resistivity is 1 over the charge carrier density times the electric charge. So either the charge carrier density or the charge has to be negative when you only had this measurement. So that's not something that you can easily understand, how electrons can have a negative density or a positive charge. And then there is one question that we haven't really addressed in the Sommerfeld or Drude model. And that is, if the electrons were free to move through your sample, then all materials should be metals. So we made here a theory for metals, but actually we made a theory that turns every material into a metal. So why do we have insulators? How can we get an insulator? And with this level of theory, that is definitely not possible. Well, Bloch then in his PhD thesis, I believe, introduced the periodicity of the lattice, and found several results that actually can explain many of the properties that within the free electron model we were not able to explain, and that we now set as open questions. And this is what we will go into next week's lecture series, where we will introduce the periodic potential, first as the weak potential, to see what then the perturbation will be on top of the states that we found for the free electron model. And then coming also from the other direction, where you say, well, we start with atoms and local wave functions, and we'll connect the two as basically some form of Fourier transform of the same picture, where we will describe free electron bands starting from atomic wave functions. Of course, you can describe atomic wave functions starting from free electron bands as the Fourier transform of those. But this is a dual representation that you can use to describe exactly the same physics. And we then can choose which is the more convenient one for the cases that we want to describe. And in both cases, it allows us to take into account more of the material specific properties. Thank you very much. Stay healthy, and we'll see each other later.